a new line. But that means having to add 1, 2, 3, 4, in this case, up to 3 times. And Babbage wanted to get it done quickly, so he pipelined the machine to do it in pairs, odd even pairs and even odd pairs. So that one turn of the crank does all 4 sets of adds for one group, and then all 4 sets of adds or transferred to the result on the last group. And he could make a machine that would be 100 columns and still be able to do staggered steps and get the answers done in 4 turns of the crank. So it was a very clever design. Any questions? Have I blown you away? That's my question. Did I leave anything out?
I think you covered everything I can think of at the moment.
What other numbers can you calculate besides the logarithm with this kind of
What kind of numbers can you calculate?
Instead of doing a logarithm table, are there any other kind of
Yes,
tables you can do?
yes, you can do trigonometry tables if you have the right starting equations. Okay, you can do actuarial tables. I mean, this whole thing could be used in many ways as long as it made use of the method of differences scheme of calculating the polynomial, and only polynomials.
There's a question back here on how we set it up, and that always comes up, so I wanted to answer it for the group.
Sure.
We have this 26-step process whereby we put the machine in different positions. First of all, we move some levers over here. But this again, we make the wheels free. Right now, the wheels are locked by the blades. So we release the blades, and then we come back and we have these manual locks on here, these silver bars that we pushed into the wheels, and the wheels are all set to 0 at that point. And then we, one at a time, pull a bar back, set the wheel to the starting value, like you would see over there, and we do all the odd ones, and then we put it in another position, and we do all the even ones. And so essentially we do exactly what Dick was showing you over there. We calculate the 7 differences, and then we put the differences in for the start point. From that point on, the machine keeps track of each one of those columns of differences with each value of x.
This particular polynomial we actually have printed out its initial set of calculations, and you can see the staggered steps all marked in blue. Since it's not just 2 columns, I mean, since it's not 4, but it's instead 8, we've got to go 2 additional staggered steps. But it's still the same mechanism. But that meant we had to have at least 4 steps. So we had to have, but it was a 8th order polynomial, so 7th order polynomial, so we had to have 8 columns anyway. We had to compute 8 answers. And from those 8 answers, we're able to compute the entire table. The beauty of this mechanism is once you've computed that initial set of answers and the table, and set the machine up with the values that are in the table to transmit their differences from one column to the next, you can run this on and on and on for hundreds and hundreds of calculations. You no longer have to figure out the remaining answers because you computed the first 8 and that's all you needed. And number 9 and 10 and 11 and everybody else from then on is automatically calculated.
And you get one answer every 6 seconds.
That's how long it takes him to crank through the 4 cycles.
Cranking speed.
He never did hook this up to a machine like a steam engine. And the reason he couldn't have done that was because if it had jammed, the machine would not have known to stop turning, and he would have actually made a mess of things. Whereas a human being he will have resistance and he'll give up.
We don't put X in though.
So
We just put the differences in.
we just put the differences in.
Yeah.
Anything else? Sorry, Stuart.
Okay, let's do 5. You know,
I've taken some of your time.
okay. We're going to run 5 cycles for these people to see because we promised that.
Okay.
Okay, that would be x equal 11 today.
Now we're working on 12.
There's 12. There's 13. There's 14.
Actually, we're doing 15 now. We're doing 15 now. This should be the end of 15. It is. Okay. And at the end of 15, would anyone like to do the chart for 15 while I read off the number on the machine?
Is there any idea of how many cycles this thing could have done within
In a
to
real-
shut down before it
Hundreds.
worn out?
Hundreds.
I mean, how practical was it if they'd actually hooked it up and started to go?
We run it twice a day. We run it at least 20 cycles. We've been doing that since last March.
Yeah, but that's a few hundred.
Actually, it's more than that. So anyway, the number I have is 3715925551.
That matches.
By the way, if you're always wondering why it ends in a 1, all the answers end in a 1. If you turn the card over and look at the initial setup, the numbers that are put in as the initial values in the difference columns are all even. And because they're all even, as you add one to the next, they always remain even. And therefore, this never gets something added to it. It stays a 1.
41.
Okay?
What are the last, I mean, I see where you're reading it off, but then the last
Oh,
set of them are
you see the
0,
neural
0.
nuts? You see the neural nuts where we are able to change the locking bars?
Yeah.
These little guys right here. We divided the machine in 2 parts. The bottom 5 digits are being used as a counter to count what we're doing. So this column actually contains a 1 at the very bottom, and then all zeros all the way across. So we keep adding 1 in at the bottom. And then these contain the actual differences for the polynomial and the result for the polynomial, starting at this neural nut, running straight across and up.
So the bottom set is counting how many times you've done
It's a
it.
counter. It's what X is.
You can set the machine to do 2 or 3 or 4 polynomials if you want.
At the same time.
You use fewer digits in the column when you do that. But you do it by keeping the carries from happening up the top.
Yeah.
So in a sense, Babbage thought of everything. I haven't found anything yet that's a flaw in this machine. However, the design for the printer did not explain how this carriage mechanism should be attached to the printer. It just simply showed what it would look like, but didn't show how it was attached. We had to figure that out. Also, like I say, it had a gear, single handle, attached to the main shaft. And when we put it together, we realized we couldn't turn it. Now, you might say, well, then this doesn't actually meet Babbage's design exactly, which is true. But there's one thing about Babbage that you probably should know. He was a guy who tinkered all the time. Everything he would work on, if it didn't work, he would change it. So if he had actually started to build this and realized, hey, I can't turn it, he would have put in his own 4-to-1 reduction gear. It's not something out of his mind. He wouldn't have dismissed it because it's not perfect. His machine wasn't perfect to begin with, and he knew that. But he never got a chance to build it to find out. We did. It works, okay? And it could be built based upon the tolerances available to Babbage in 1847. So that's a testament. But it never got used in any of our development of computers.
And this one is built with the metals and the materials that were available to Babbage at that time. The Science Museum in London did significant research into materials. They had the beautiful fragment and they knew what materials were in it, and historians know about materials in that time frame. So it's really, it could have been built in Babbage's time.
There's another handle at this end, which was not part of his design, because when you were working on the printer, you were supposed to do everything from that end. Except that what we discovered was that if you're working down here, you don't want to have to run down there and crank it through a cycle. You'd rather be able to just do everything with the printer at this end. So you do it here.
So they put a clutch in there to disengage the printer from the calculating mechanism while they were working on
Just run the printer by itself.
But we'll stand by for questions.
And meanwhile, Stu's got a tour to do. Anyone who wants to go on the 2:30 tour, it's starting late. It's probably going to be an hour and a quarter tour. You're welcome.
This is a Babbage.